Hey everyone, welcome. Today we're diving deep into a chapter that's not just in your textbook, but literally all around you, metals and nonmetals. This is Chapter 3 from your Class 10 NCERT science book, and trust me, it is an absolute goldmine for your board exams, so let's get into it. You know those questions in the board exams that can make or break your score? Well, a lot of them come from this very chapter. That's why in this explainer, we're covering everything. All the key concepts, the important reactions, and especially those tricky little exceptions. By the end of this, you're going to be ready for anything they can throw at you.
All right, ready to do this? We're not just going to learn this chapter, we are going to completely master it. Let's begin.
Okay, first things first. How do we even start to tell these elements apart? Well, the easiest way is to just look at them. We check out their physical properties, how they look, how they feel, and how they behave. These are the telltale signs that give us our first clues. Let's kick things off with a property called malleability. Ever used aluminum foil? That's just a chunk of aluminum that's been hammered into an incredibly thin sheet. That's malleability right there. And for your exams, the two you really need to remember as the champions of malleability are gold and silver. Next up, we've got ductility. This is all about stretching metals into thin wires, kind of like the copper wires you see everywhere. And get ready for this because it's an amazing fact. Just 1 tiny gram of gold can be stretched into a wire that's 2 kilometers long. That's just wild. All right, time for a quick-fire round of other key properties. Metals are lustrous, that's just a fancy word for shiny. They're usually hard, but, and this is a big but, not always. Alkali metals like sodium are so soft you could cut them with a knife. Metals are also fantastic conductors of heat and electricity, with silver and copper being the best of the best. That sound a bell makes when it rings? That's because metals are sonorous. And finally, they're all solid at room temperature, except for our famous little rule breaker, mercury. Remember these exceptions, they are absolute gold for exams. So, here's a handy side-by-side that makes it all super clear. But the real secret to acing this topic is knowing the exceptions for nonmetals. Most are dull, right? But iodine actually shines. Most are soft, but diamond, which is just carbon, is the hardest natural substance we know. And while they're usually terrible conductors, another form of carbon, graphite, actually conducts electricity. Mastering these exceptions is what's going to make your answers really stand out. Okay, so looking at physical properties is a good start, but there are just too many exceptions. To get a really solid, definite way to classify these elements, we've got to look at how they react chemically. This is where the real story is. So what happens when a metal meets oxygen? Simple, you get a metal oxide. Now, these oxides are usually basic, but, and here's a super important concept for your exams, some of them are what we call amphoteric. It's a fancy term that just means they can act like an acid and a base. The two you absolutely have to remember are aluminum oxide and zinc oxide. Seriously, write those down. This all leads to a really big question. If you burn a magnesium ribbon, you get this brilliant, dazzling light. But if you heat up iron, it just kind of glows red. And gold? It does nothing at all. So does that mean all metals react the same? The answer is a huge no, and this difference is the key to pretty much everything else in this chapter. And the answer to that question is right here in the Reactivity Series. I want you to think of this as the master key for this whole chapter. It's just a list that ranks metals from the most reactive, like potassium at the very top, all the way down to the least reactive, like gold. If you can memorize this series, you'll be able to predict how so many different reactions will turn out. It's basically the ultimate cheat sheet for your exam. So we know metals react differently, but why do they even bother reacting at all? Well, it all comes down to their electrons. See, every atom has one goal in life, to get a full, stable outer shell of electrons, just like the noble gases. They're kind of like the cool, unbothered kids of the periodic table. Let's look at a classic chemistry story, how we make table salt, or NaCl. Sodium has this one extra electron that it's just dying to get rid of, and chlorine over here is just 1 electron short of being complete. It's a perfect match. So sodium transfers its electron over to chlorine. Sodium becomes a positive ion, chlorine becomes a negative ion, and you know what they say about opposites? They attract. That powerful attraction creates a really strong ionic bond. It's a simple game of give and take. Now, because that bond is so strong, ionic compounds have some very specific properties. And you can bet this will be an exam question. They're hard, brittle solids, and they have super high melting points because you need a ton of energy to break those bonds. They usually dissolve in water too. But here's the most important part.
As solids, they do not conduct electricity because their ions are locked in place. But if you melt them or dissolve them in water, the ions are free to move around, and suddenly they do conduct electricity. Remember that distinction.
Okay, so we get how metals react, but let's get practical. How do we actually get all these useful metals out of the ground in the first place? Well, that whole massive industrial process has a name: metallurgy.
The definition is pretty straightforward. Metallurgy is just the A to Z process of taking a rock that contains metal, which we call an ore, and doing everything it takes to end up with a pure, shiny piece of metal.
We can actually break this huge process down into 3 main steps to make it easier. Step 1, concentrate the ore. This just means getting rid of all the useless dirt and sand mixed in with it, which, by the way, has the cool name gangue. Step 2, extract the metal from its compound. And step 3, refine it, which is basically the final purification step to get it super pure.
Now, during that extraction step, you absolutely have to know the difference between 2 key processes, roasting and calcination. Both are about heating the ore to convert it into a metal oxide, which is easier to work with. The key difference is this: roasting is for sulfide ores and you need lots of air. Calcination is for carbonate ores, and you need very little or even no air. A good way to remember is S for sulfide and roasting, C for carbonate and calcination.
And here is where it all clicks into place. The method we use to extract a metal is tied directly to, you guessed it, the reactivity series. The super reactive metals at the top are really stable in their compounds, so we need the brute force of electrolysis to break them apart. The metals in the middle aren't as tough, so we can just use carbon to reduce them. And the lazy, unreactive metals at the bottom, like gold and silver, we often just find them in their pure native state, no major extraction needed. All right, so we've extracted our pure metal. We're done, right? Not quite. Now we've got a new problem. A lot of metals want to react with the air and water around them and start to degrade. This brings us to our final section, the problem of corrosion and the ingenious solution of alloys. You can think of corrosion as the metal basically trying to turn back into the more stable, earthy compound it started as. The most famous example, of course, is the rusting of iron, but you also see it all the time with the black tarnish that forms on silver or that green coating you see on old copper statues. So how do we stop this from happening? Well, the main idea is to create a barrier between the metal and the environment. This can be as simple as painting it or putting some oil on it. But one really clever method is called galvanization. Here, we coat iron with a thin layer of zinc. Now, since zinc is more reactive than iron, it corrodes first, essentially sacrificing itself to protect the iron underneath. It's like a tiny metallic bodyguard. But maybe the smartest way to prevent corrosion is by alloying. An alloy is just a uniform mixture of metals or a metal and a non-metal. And this does more than just stop rust. It can totally change a metal's properties for the better. Think about it. Pure iron is actually pretty soft. But mix it with a little carbon and other elements and you get stainless steel, which is hard, strong, and doesn't rust. It's like giving the metal superpowers. And that leaves us with one final thought to chew on. We think we're surrounded by all these different metals, but now we know that so many of them are actually alloys. So the next time you pick up a coin or a fork or even just your keys, ask yourself, is this a pure metal or is it a cleverly engineered alloy in disguise? It's a great reminder that chemistry isn't just in a book. It's absolutely everywhere.